Alright, so in this video, I'm gonna be explaining another important article with the title pairnorm, tackling oversmoothing in GNNs. This ICLR paper in 2020. The performance of graph neural networks is known to gradually decrease with increasing number of layers. This decay is partly attributed to oversmoothing, where repeated graph convolutions eventually make node embedding indistinguishable. It's like you apply, for example, a filter on an image, and the image becomes blur and blur so that all pixels look the same, and you lose all information. So our main contribution is pairnorm, a novel normalization layer that is based on a careful analysis of graph convolution operator, which prevents all node embeddings from becoming too similar. What is more, pairnorm is fast, easy to implement without any change to network architecture, nor any additional parameters, and is broadly applicable to any GNN. So experiments on real graph demonstrates that pairnorm makes deeper GCN, GAT, and SGC models more robust against oversmoothing. So it's just a normalization layer. So we introduce a normalization scheme that makes GNN significantly more robust. Our proposed scheme capitalizes on the understanding that most GNNs perform a special form of Laplacian smoothing, which makes node features more similar to one another. The key idea is to ensure that the total pairwise feature distances remains a constant across layers, which in turn leads to distant pairs having less similar features. So to understand oversmoothing, among these perhaps the least understood is oversmoothing, which is indeed lacks a formal definition. For example, in 2018, they showed that the graph convolution is a special case of Laplacian smoothing. The standard form being like this, the graph convolution lets gamma equal to 1 and uses the symmetrically normalized Laplacian to obtain x tilde. This smoothing allows the node representation within the same cluster become more similar, and in turn helps improve SSNC performance. Another way of thinking about oversmoothing is as follows. Repeatedly applying Laplacian smoothing too many times would drive node features to a stationary point, washing away all the information from these features. So pi is independent of the values of x sub j of input feature, and is only a function of graph structure, for example, the degree. So Laplacian oversmoothing washes away the signal from all the features, making them indistinguishable. We will refer to this viewpoint as feature-wise oversmoothing. To this end, we propose two measures, rho diff and col diff, to quantify these two types of oversmoothing. So these are two measures to see, for example, the L2 distance between the two nodes. So the ith row iris column of H sub k. And the row diff measure is the average of all pairwise distances between node features, rows of the representation matrix, and quantifies node-wise oversmoothing. Whereas column difference is the average of pairwise distances between L1 normalized columns of representation matrix and quantifies feature-wise oversmoothing. So one of them is node-wise oversmoothing, the other one is feature-wise. Although oversmoothing can be a cause of performance drop with increased number of layers in GCN, adding more layers also leads to more parameters, which magnify the potential of overfitting. In order to decouple the effect of oversmoothing from these two factors, we study oversmoothing problem using SGC model. SGC is simplified from GCN by removing all projection parameters, simple graph convolution. Just remove all projection parameters of graph convolution and all nonlinear activation, then it becomes a simple graph convolution. And the K here is just the number of graph convolution. So A to the K, if you remember one of the articles that I explained, it was diffusion. So you add these theta, so it was like this theta A to the I. So different powers of the adjacency matrix helps to help the random walk to discover different far transitions, more than one hop transitions. So it could capture some global aspects. Note that SGC has a fixed number of parameters and does not depend on the number of graph convolutions. In effect, it is guarded against the influence of overfitting and vanishing gradient problems with more layers. So it guards against this vanishing gradient just because you are removing nonlinearity. You know, when you have a deep neural network, it has vanishing gradient problem. That's why people, for example, use skip connections or residual nets or different methods. But here we remove the nonlinearity. Of course, maybe you may think, okay, I may lose expressivity, but doesn't matter. At least you don't have this performance degradation for vanishing gradient. So this leaves us only the oversmoothing as a possible cause of performance degradation with increasing K. So the simplicity of simple graph convolution does not seem to be a sacrifice. It has been observed that it achieves similar or better accuracy in various relational classification tasks. For example, if you improve the layers, the accuracy will go down. And the loss will improve as you improve the layers. So the dashed line is the best performance, best in color SGC performance with increasing graph convolutions on Cora dataset for each K with trained SGC in 500 epochs. 500 epochs save the model, because it has many local minima. We want to get rid of that. So you need to have more epochs because it's very difficult to get the global. So maybe they reduce their batch size but increase their epoch so that you can get to this. Gradually you can get to this. So the proposed pair norm is very simple. We start by establishing a connection between graph convolution and optimization, that is graph regularized least squares. And let X bar be a new node representation matrix depicting ith row. So we want to, the GRL as problem is, we want to minimize this distance. So the bar is the new node representation. But at the same time, we want to minimize the distance between two. I mean, in the new node representation between the two I and j, because I and j belong to the same edge. Here we are summation is over edges. And so the first term can be seen as total degree weight least squares. The second is a graph regularization term that measures the variation of new features over the graph structure. The goal can be stated as estimating new denoised features that are not too far off the input features and are smooth over the graph structure. So it has a closed form solution. So it's very smooth because and our smooth over graph structure, you're reducing big gradients. The optimization problem here in 5 facilitates a closer look to if it is an edge, if there is not an edge, we want them to be, for example, here and here. Because there is no edge between this one and this one, we want the distance between them to be far, to have big distance. So that's why we have this minus and then the distance. So if we increase the distance between them, it is good. If increase the distance between them, I mean the L2 distance, then it is good. But if they are an edge, the opposite thing. For example, we want these things to be very close to, similar to each other. So that's why there is a positive sign here. And of course, we want the representation of all to be similar to the new one. This is also interesting. That's it. That is, the rest of them is just some analysis. So comprising centering and rescaling steps. First you center, then you rescale it. So in summary, our proposed pair norm can be written as a two-step. First we center, then you scale it. You center and then you scale it. And you see the effect on that Cora layer, Cora dataset. And for PubMed dataset, we have accuracy of 71%.